Hello, we are live. So let's continue with the material we started talking about on Wednesday. Before we get started, can you give me a thumbs up that everything is working fine on your side there? I can see a couple of people are still streaming in to the room. So let's do a little bit of small talk. How's everyone feeling today? A little bit stressed out because of midterms, I imagine. Either for this class or, of course, for the other classes. I imagine you may have some other midterms this week. Um, so I do want to remind you that there's office hours on Tuesdays and Thursdays. And it's at, if I remember correctly, it's at 3 p.m. Central Time. So it's at the same location here. If you go in the back of the auditorium, if you go out there, you'll get to the library, and then from there you can get to the physics office's virtual space, where you can then find me during office hours. So had a couple of people show up in the recent weeks, and of course I'm happy if you have any questions for you to show up. So okay, with that, I think everyone's here now. Just not hitting the 100 mark today. So we're going to talk today about the remainder of the chapter 7 about work and kinetic energy. And just as a reminder, work is the energy transferred to an object by a force working on it. And if you recall, that is equal, as we derived or as we defined, work W is for a constant force is force times displacement. As a vector product, a dot product between two vectors. So this is for constant forces only. If we don't have constant forces, then we would have to change that expression a little bit, and that's where the integrals come in. Notice that this can have any sign, right? We can have positive work, negative work. It just depends on the orientation of those forces with respect to the displacement. And if they're pointing in opposite directions, then we'll get a negative dot product. So that's work. Work, again, the energy transferred to an object by a force working on it. The other thing we introduced last time on Wednesday was kinetic energy. That's the energy of a moving object by virtue of its speed. I see someone correctly points out that this is lesson 16, not 15, but don't worry, I'm not going to cover the same material as on Wednesday. So I just forgot to update the title slide. Don't worry about that. Did I also not update the stream? I guess I didn't update the stream either. The kinetic energy is the energy of an object by virtue of its speed, and so we introduced an expression for that. Kinetic energy. Give it the symbol K. And that is 1/2 mv squared. So this is a quantity that depends on the mass and the speed, or the velocity if you wish, but since we square it, the direction doesn't actually play a role. And this will always be positive, or I guess zero, only zero if the speed is zero. So this is always a positive quantity. Now some things are interesting about this. If we are thinking about kinetic energy as something that depends on the speed, this will depend on the reference frame, right? We can go into a reference frame that is moving with respect to the first reference frame, and our speed will change, and that will change the kinetic energy in that reference frame. But the same thing is actually true for the work, since the displacement can change, right? So one of the examples that the textbook uses is we can have a person moving in this direction in a moving train, so moving along the direction of the train. So that will give that person a higher total velocity with respect to the ground than if that person was walking in the opposite direction in that train. In this case, the velocities would add up as vectors, and we'd end up with a velocity that is smaller in magnitude, and so the speed would be smaller in the second case, assuming the person doesn't run so fast compared to the train that it actually increases the speed. So the kinetic energy of the person with respect to the train might be the same if the magnitude of the velocity with which the person is walking in the train car, if that's the same, then the kinetic energy will be the same with respect to the train, but it won't be the same kinetic energy with respect to the ground. So that will play a difference. So we have to make sure we're thinking in the right reference frame here. So those are the two concepts we introduced on Wednesday: work and kinetic energy. And now, of course, we're going to relate those to each other. And that's going to be the work energy theorem, which combines these two concepts: work energy theorem. So how do we derive that? Well, let's think back about the infinitesimal amount of work that is being done by the net forces. So let's introduce dW net, which is the work done by the net force. Work done by the net force. So that could be a sum of different forces that together forms the net force. But this net force will be something we can construct from all the forces that are playing a role in this particular situation. So that dW net, the infinitesimal amount, the infinitesimal net work done by the net force, is, by our definition of work, is the net force dotted with the displacement. And since we're talking about infinitesimal amounts, we're going to use displacement dr. Now we know what the net force is, because the net force causes acceleration. So the net force will be the mass times that acceleration, or it will be the mass times dv dt, right? The derivative of the velocity, which is the acceleration. So we can replace that in this expression. We'll end up with m dv dt dot dr. And now we'll do something that is that physicists like to do and that mathematicians always cringe at, which is we're going to think about these dv's, dt's, and drs as independent. So instead of thinking of dv dt as a derivative, we're going to think of that as the ratio of dv over dt, which really is pretty close to what a derivative is. It is the infinitesimal change in the velocity divided by the infinitesimal change in time over which that change in velocity happened. But if we think about these three things as independent quantities, we can actually move the dt over to the dr side. And we can rewrite this as m times dv dot dr dt. And if we do this, then dr dt, that's our v. This is equal to our velocity itself. So we end up with m v. I'm just going to change the order of the terms here, of the factors. So we have mv dot dv. So that's going to be our work, infinitesimal work done by the net force. So a couple of things that we can see from this: if the velocity is perpendicular to the change in the velocity, In other words, if it's perpendicular to the acceleration, if the velocity is perpendicular to the acceleration, then the net work, the infinitesimal amount of net work, will be equal to 0, right? Because of the dot product. And that's exactly what happens in uniform circular motion. If we have uniform circular motion, or acceleration is pointing towards the center, or velocity is pointing tangentially to the circular motion. And so in this case, the net work will be equal to 0 at an infinitesimal, in an infinitesimal sense. And so this is going to, that's something that we already concluded before. So all of this is still in infinitesimal quantities. So now we're going to want to turn this back into macroscopic finite quantities. So we're going to determine the net work as the integral from some point A to a point B of the infinitesimal net work, not net worth, net work, net work, not network, net work. There's a space there. So that is now equal to the integral from A to B of mv dv. And again, we're going to do something that physicists like to do, is we're going to think of these v's, even though they're multiplied in a dot product, we're going to just think of that as single numbers, not as vector quantities. And in that case, this will be the integral of, or that integral will be 1/2 mv dot v evaluated between A and B. And since this is equal to the speed squared, that will be 1/2 mvb squared minus 1/2 mva squared, or the kinetic energy at B minus the kinetic energy at A, or the change in kinetic energy. So there's a couple of places where we do the kind of physics approach to calculus here. One of those is when we move the dt over to the dr, and then another one is where we do this integral here without necessarily while using the vectors as a dot product. All of that, of course, is correct, but it is a little bit of an approach to calculus that would need a little bit more work to prove beyond any mathematical doubt that this is exactly true. And I'm not going to go through that. You can just sort of see that this all makes sense. You could, in particular for this last step here, you could write this out in its terms. So you would have, for example, the integral from A to B of mvx dvx plus mvy dvy plus mvz dvz, and you can do this integral individually for each of those three terms, and then you would put everything back together and you'd find again that you have the kinetic energy. In any case, the conclusion, which is the work energy theorem, is that the net work, or in other words, the total work done by the net force, is going to be the change in kinetic energy. If a force does work on a system, and in other words, if that force transfers energy to that object or to that system, then the amount of energy that is added to the system will be the change in kinetic energy. If the energy is added to the system, the kinetic energy will go up. If energy is removed from the system, or the net work by a force is negative, then the kinetic energy will go down. And now you might wonder, well, why would we want to use this? Well, one thing that is actually convenient about this expression is that it doesn't involve any vectors. So anyone who likes doing things with scalar quantities instead of vector quantities will like this expression because it typically allows you to simplify the problems if you use the work energy theorem. So look at an example of a mass that is sliding down a inclined plane. So we have a mass m, and there's a force due to gravity, so the weight is working vertically downward, and there's a normal force that is perpendicular to the inclined plane. Let's assume there's no friction. So this is inclined plane with no friction. So what will happen is there's going to be a net force that's going to be pointing downwards to the slope. So that's our net force, and that will be proportional to our acceleration, right? So if that is going to be our acceleration, we could introduce a set of let's call the coordinate along the slope s, and let's introduce a coordinate system x, y. Now, for once, we're not going to pick as a rotated coordinate system. So what we could do is, as we've done in chapter, I don't know, chapter 6 or chapter 5 even, so we could determine this acceleration. This acceleration will be the component of the weight that is along the s direction. So the acceleration will be, as a magnitude, the acceleration is g times the sine of theta. So that's our horizontal component, excuse me, not the horizontal component. This is the component of the weight along the slope. So with that acceleration, we can then use our expression v squared final is v squared initial plus 2 times the acceleration times s final minus s initial. And the one thing I've forgotten here is that this acceleration is of course going to be negative because it's pointing in the opposite direction as the s axis. So that is going to be vi squared minus 2g sine theta times s final minus s initial. So the reason why only g plays a role in this acceleration is because we know that the object is moving along the slope, and so the normal force is not going to have any impact. Why is there no m? So this is, the weight is mg, and that is going to be our net, or that is going to give us our net force, but that is equal to the mass times the acceleration. So the mass will actually drop out again. So if you go through the full Newton's second law derivation, you'll see that the mass drops out, and of course it has to, because we know that the acceleration here is the thing that that needs to go into that formula and be multiplied by with the change in the coordinate s. So now let's see how we would solve a problem like this with the work energy theorem. In the work energy theorem, if we have an initial and a final state, we can write that the net work is going to be equal to the change in kinetic energy. So what's the net work? It will be the work due to the weight plus the work due to the normal force. Now, one thing we've talked about last time is that the work done by normal forces is always 0. Why is it 0? Because the normal force is always perpendicular to the displacement. Let's call it dx. So the normal force is always perpendicular to the displacement. So the work done by the normal force is 0, and the only work in this net work is due to the weight. In the kinetic energy, the change in kinetic energy we can immediately write as 1/2 mv final squared minus v initial squared, right? That's just using kinetic energy, taking the difference in the initial between the initial and the final state. So let's focus on our work done by the weight. So that's going to be the force dot the displacement. And in this case, our displacement or force is going to be vertical. So this has only y components. So this will only only the y component of the displacement will play a role. So this will be minus mg times y final minus y initial. So if we put this all together, this has to be equal to that. The change in kinetic energy has to be identical to the net work done by the force of gravity, by the weight. And so we can put everything together here. We'll see that 1/2 mv final squared minus v initial squared is equal to minus mg y final minus y initial. Now, one of the things you'll see is that these masses drop out. We can rewrite this putting the 2 on the other side. So v final squared minus v initial squared is minus 2g y final minus y initial. Or the final velocity is the initial velocity minus 2g y final minus y initial. This is already looking pretty close to the expression that we had before. The only difference is that we have now our y final minus y initial instead of sine theta times s final and s initial. But you'll see that our the connection between the s coordinate in this direction and the y coordinate in this direction is just multiplying by a sine of theta. So that's going to give us the final step here. The final velocity squared is the initial velocity squared to minus 2g, and then we have yf is sf times sine theta and si times sine theta. I'm just going to put that at the end here. So why is it minus mg here? That's because the force is, of course, going in the negative y direction. So that's why there's a minus sign there. Okay. So that's an example of how we can solve this kind of problem with the work energy theorem. The only thing we needed to know is the work. I mean, writing down the change in kinetic energy is easy. That's always going to be the same. It just involves scalar quantities and the velocity, or the speed, actually, only. The net work, in this case, only depended on one force, which is constant. So even though other things might be changing, that's the only force that matters. And that allowed us to write down this expression just like the one that we derived earlier with the full treatment with Newton's second law. So let's apply this to a different problem now. And the problem that we're going to apply it to is, again, something that if we actually were in class, I would show you, but because we have a setup for that, but of course I can't. But it is, consider it a marble racetrack where we let a marble roll from the hill and it goes through the loop, and then it comes out the other side, of course. So the question now is, at what height do we have to let the marble start? We have to let it go from rest so that it makes that entire loop. So it doesn't, end up here and roll back, or it maybe gets 3/4 up and then it falls down. So at what point, at what height do we have to let the marble go so it makes that entire loop? Now this is different from this inclined plane because now the normal force will change everywhere along this trajectory. The normal force here will be pointing towards the center because the normal force together with the gravitational force will be what causes the centripetal acceleration to make this go into a circle. But the normal force will be larger here at the bottom. It will decrease. There will be some normal force at the top, and then the normal force will increase again as we get as the marble continues in this loop. What's the only time when the normal force will be 0? That's exactly at the point when the marble starts to leave the track. That's when the normal force will be 0. At any other time, the normal force will be positive, pointing inwards towards the center, or normal to the trajectory. But we know that because the normal force is normal to the displacement at every point, it will not contribute to the work at all. So we don't have to know anything about the normal force to solve this problem. It's always going to be a force that's normal to the displacement, so it will never contribute to the net work. The only force that contributes to the net work is the gravitational force, the weight on this marble as it's rolling down the track. So we can immediately write down the net work. So the loop problem. So we can immediately write down the net work, which is just the work done by the weight, and it's the exact same expression we wrote down in the previous problem. It's the same work. It's the same weight times the displacement in the vertical direction because there's a dot product. So we already have our net work. Now, what will be the net work until from between the point V1 here and the highest point? Well, we can actually plug in our Y2, which is going to be 2R, and we're going to solve for Y1. So this is going to be minus mg. So I think this is my Y2. This is Y1. So that's mg times 2R minus y. Let me try to write y1. So that's our net work. We can also write our changing kinetic energy. It's 1/2 m v1, v2 squared minus v1 squared. That's the change in kinetic energy. But because we start from rest, that v1 is equal to 0. So that will be 1/2 m v2 squared. Okay, so we want to calculate the height, y1. We know that this is going to be equal to this, the kinetic energy at point v2. Can we calculate the velocity v2? Actually, we can. So let's think about how we calculate that velocity. We can actually relate that to the net force at the top and relate it to centripetal acceleration. So there's going to be a centripetal acceleration at the top at point 2 here. That's related to the sum of the two forces applying on the marble there, the normal force and the weight. So the normal force plus the weight will have to be equal to the centripetal acceleration times the mass. So the normal force plus the weight is equal to the mass times the centripetal acceleration. And we know that centripetal acceleration is v squared over r. So that actually gives us a way to get to v squared, right? We can use this to write v squared, v2 squared is r times, let's make sure we So n plus mg over m times r. That's going to be your v2 squared. So we can now plug in our v2 squared here, and then set those two parts equal, and that will give us an equation, right? So delta k is the net work done, will give us the expression that 1/2 m times v squared, so times r n plus mg over m, is equal to minus mg 2r minus y1. And now we can think about what is actually happening here. So there's going to be a little bit of simplification first. So 1/2 r n plus mg, because those m's drop out here, is minus mg 2r minus y1. So remember what I said, that at the time, at the point when the normal force becomes 0, that is when the marble will fall away from the track. So as long as the normal force is positive, we're still going to be moving on the track. So n has to be equal to 0, has to be greater than 0. And if n is exactly 0, then y1 will be the minimum height required to maintain n greater than 0. So someone's pointing out, should it not be minus g, not minus mg? I should have mg here. So the thing you can always do is compare your units, right? I have m times g times the distance on the right hand side. I have m times g times the distance on the left hand side. Or I have mg, which is a force, times the distance on the right hand side. And I have normal force times r, which is again the same product. The units match up on both sides for all of the terms. So let's solve this equation now for n equals 0. If n is equal to 0, then we find 1/2 r mg is minus mg 2r minus y1. This is now the minimum value for the height. And now, of course, we can rewrite this again. Mg is now going to drop out, so we end up with 1/2 r plus 2r is equal to y1 min. So the minimum height is 5/2 r. We have to have at least a height above the loop that is 5/2 r, or in other words, 2 times the radius plus another half times the radius. So we have to start 1/2 radius above the top of the loop for this to make a full revolution there. So the conceptual part here is that the time that the normal force always has to be positive if we want to maintain contact with the track. As soon as the normal force becomes negative, now a normal force can't be negative, it's always pushing from the object against the direction, from the track against the marble. So the normal force has to be positive, and as soon as it becomes 0, that's when the object will lose contact with the track. So there's a couple of other problems we can do with this. There's, for example, the stopping force. So if we have an initial velocity, let's say we shoot a bullet at a set of wooden boards. That is not a demo that we do in class typically. But if we were to do that, you would see the bullet stop at a certain distance into the boards. That distance multiplied with the unknown force with which we're stopping this bullet must be equal to the change in kinetic energy. So if we know the initial velocity, we can calculate the initial kinetic energy. The final kinetic energy is 0. So we have the change in kinetic energy is going to be the total initial kinetic energy. And that has to be equal to the force times the distance, which is the work done on this bullet to stop the bullet. So again, we can use that then to calculate the magnitude of the force that is stopping the bullet. You wouldn't need the weight of the bullet here because, actually you would need the weight of the bullet. Sorry, I correct myself. So in terms of stopping power, we can actually quickly do this problem, right? Stopping, let's call it stopping force actually. So the change in kinetic energy is 1/2 mv squared. The net work being done is force times displacement. So the force will be, and these of course have to be equal to each other. So the force will be 1/2 mv squared over the change in over the stopping distance. So yes, you would need the weight of the bullet. Okay, so one final concept for today is power. And power is essentially it is the work done per unit time. So let me go back to the slides actually, to the whiteboard. So power is work over time. Let's write this sort of like this. So power is, for example, a finite amount of work done over the time it takes to do that work. So this would be average power. Instantaneous power would be the derivative of the work with respect to the time. So this is, this comparison between average and instantaneous is of course something we've seen before, right? So if we think about that, if this is the derivative of W of the work with respect to the time, and we know that the work in the case of constant forces is F dr, and actually in the case of infinitesimal elements we can write this as an exact quantity for infinitesimal amounts of work. So then the power will be dW dt, which will be F dr over dt, or force dot dr dt, which is force times velocity. So if we have a force that's in the direction of velocity, then we will have that force exert power or essentially do work over time. If the force is perpendicular to the velocity, if we have a velocity in this direction and the force is in this direction and it's in the perpendicular direction, then the power is 0, because this force is not doing work at any time. So the power will be 0. Again, this is going to be a useful quantity to think about. If we know the power, for example, we can calculate it because it's force times velocity. We can then calculate the average power or the instantaneous power if it is constant. We can use that to calculate the amount of work done in a finite time, and then we can use that to calculate, for example, the change in kinetic energy, or we can calculate the work that has been done by other forces. So if we look at, for example, this situation where we have a car driving up a hill, so the force of gravity is working on this car. So the force is pointing down, the velocity is pointing slightly upward. So the force, the power of gravity will be negative, which means that the car itself has to provide that power to drive up the hill. Or in other words, the car has to provide that power through the force in through the propulsion system of the car, through the engine. So if we now can calculate for this particular slope and this particular velocity with the force due to gravity, if we can calculate the power, then we can say if this car has been driving for, let's say, 15 seconds, what is the amount of work, the total amount of work that has been done by gravity. So in this case, so car up a hill, so the force times the velocity, which is the power, will be minus mg times the velocity, which in this case was a constant velocity v0, times the cosine of the angle between the force and the velocity. So that's going to be the slope, the 15% grade, plus 90 degrees, because the force is vertical and this slope is with respect to the horizontal. So that's going to be the cosine of 90 degrees plus the inverse tangent of 15%, which is the angle corresponding to the slope of 15%. So that gives us our power. And if we now have an interval delta t, p delta t will give us the total work, the work done by gravity during interval delta t. So yes, the units of power are going to be in watts. So that's in watts. Yeah, I apologize on behalf of generations of physicists that we keep reusing letters, and so the work and the units of power are the same. It's W, so don't mix those up. Don't think that work is in units of watts, but this is in watts, and that's in since this is going to be work per second, that's going to be joules per second. So someone's asking, where does this percent come from? That's just a definition of this 15% grade. Of course, they could have made the problem just a little bit simpler by saying that this is a 15-degree slope. Then we would not have had to put that percent there. Then we would have just had an angle of 15 degrees. But in this case, they're putting the percent there so that they can, I guess, introduce the inverse tangent to get from grade to an actual angle. Okay, that is it for today. So I hope you all have a good weekend, and I will see you all on Monday. And so one last question that someone's asking: yes, you can of course convert this cosine of 90 degrees plus that angle into the sine of that angle, which would be the next step.